Hi everyone, I'm Suhaila Saleh from the University Technical Malaysia Melaka. In this video, you will learn how to find solutions to linear system using Gauss elimination with partial pivoting. Gauss elimination is a fundamental direct method. With the absence of rounding off and error calculations, this method will yield the exact solution in a finite number of elementary row operations. The basic idea of Gauss elimination with partial pivoting process is to solve the equivalent system, which is in a simpler form compared to the original linear system, and also to avoid having the pivot element near to zero, since this may cause division by zero after normalization. Now, a set of simultaneous linear equations can be expressed in the form as shown in the slide. A linear system is firstly rewritten in the matrix form. This is then transformed into what we called an augmented matrix. Row reduction is then operated. However, the key step here is to ensure that the pivot element is the largest absolute value among entries underneath it. This is done by either interchanging any two rows or using row replacement operations. This is then followed by back substitution until all solutions are found. Let's take a look at an example of Gauss elimination with partial pivoting. Example 3.5 shows how to find solutions for a system with three simultaneous equations. The solutions can be calculated, and the values to be found are x1, x2, and x3. These would be exact values if the solutions are remained as fractions. The linear equations are firstly rewritten in augmented form. Just as in Gaussian elimination, we want to reduce the system into upper triangular form, where the first row will be taken as pivot row, and the first entry of the first row will be the pivot element. Looking at the first column, the largest absolute value lies in the second row, which is 3. Therefore, applying Gauss elimination with partial pivoting, row 1 and row 2 are interchanged to ensure largest absolute value to the pivot element. Next, elementary row operations are carried out so that all entries under the pivot row are zeros. Then, row 2 will be the pivot row. Looking at the second column and second row downwards, the largest absolute value lies in row 3, which is 7.0033. Hence, row 2 and row 3 are interchanged to ensure largest absolute value to the pivot element. Next, elementary row operation is carried out to row 3, which is row 2 multiplied by 0.0271 and added to row 3. This is to reduce the entry under the pivot element to 0. Finally, through back substitution, the solutions are calculated, where x1 is found to be 2.9987, x2 minus 2.5007, and x3 6.9804. Let's take a look at another example. Example 3.6 shows how to find the solutions to the system of linear equations using Gauss elimination with partial pivoting. The system is firstly rewritten in augmented matrix form. Looking at the first column, the largest absolute value lies in the second row, which is 4. Therefore, applying Gauss elimination with partial pivoting, row 1 and row 2 are interchanged to ensure largest absolute value to the pivot element. Next, elementary row operations are carried out so that all entries under the pivot row are zeros. Then, row 2 would be the pivot row. Looking at the second column and second row downwards, the largest absolute value lies in row 2, which is 1. Hence, no interchange is necessary. Finally, through back substitution, The solutions are calculated and x1 is found to be -3, x2 is found to be 3, and x3, 1.